All right, please take your seat. I know there's still like 50 people outside. Okay, I think, we should probably get started. And as always, use the link that is up here to type your questions in. All right, so it's my great pleasure to moderate this panel on creativity, novelty, and emergence. So we had 3 speakers earlier today, and they're joined by 2 faculty from the University of Michigan. So when you start answering your first question, so please, give a little bit of your background, right, so that people get the context. All right, so I have a few questions here that I'm going to read out, and then we'll go through the panelists, and then I'll also invite some questions from the audience. Okay, so the first question, I think all of you can take a crack at it, is can human intelligence be computationally recreated? All of it or parts of it, whatever you feel, either all of it or the most valuable parts, right? If so, is it tractable in the coming decade? And are there limits, right? If you don't agree that they can be recreated, what is your opinion on the limits? Okay. So Lou, can we start with you? And maybe a little bit of background on your research as well.
Right. Okay. So I can start. So I feel like it sounds like, we're talking about like whether we're able to achieve AGI or maybe even ASI. So I think it's theoretically possible if we're given enough amount of compute plus the right, type of data and environment to learn those things. And that said, it's unclear whether the current, compute will grow in the same speed as like how we'd like to achieve human intelligence. And another need is that we should have a better or deeper understanding of how human intelligence is like, including how, say, how human understand, create all those cognitive processes. So far there are a lot of progress, but I feel like there's still a lot of things to do. But I'm optimistic those are totally possible if we can do that. So that's my understanding. I'll give other panelists to talk about it.
Yeah, just a quick interjection. You mentioned that we're limited by compute. You did not say anything about data. Is that?
Oh yeah, that's a good point. I kind of like integrate data and environment together because my understanding is like, training on static data has so much, to do. So in the future, we have to think about, humans don't just like read and learn those things. We interact and the richness of the environment and, even through simulation, those things will need to be taken into consideration.
Thank you.
Yeah, so I don't think there's anything in principle stopping us from recreating all of human intelligence and even going beyond it. But the ways that we're doing it might not be the ways to get there. So just to throw out some numbers, right? We train our current language models on order 10 trillion tokens or words. How many words do we get in our lifetime? 100 million. For us to read 10 trillion words, it would take us 240,000 years. So we're very data efficient. You might think that we had 500 million years of vertebrate brain evolution to fine-tune our architecture, but that's communicated to us through DNA, which is only about 700 megabytes, which is equivalently 600 million words. So the combination of nature through our DNA and nurture through our experience is minuscule compared to what AI systems get. You might imagine that we also have vision, but it's not clear how much looking at trees will help us solve the standard model of particle physics. Anyway, there's a huge data discrepancy, and also we operate on 20 watts. It's not at all obvious how we can reduce the sample complexity of LLMs and general AGI by 5 to 6 orders of magnitude, and the energy consumption also by 5 to 6 orders of magnitude. And in that game plan, like achieve intelligence, the way we're doing things right now. At the same time, it's remarkable that training on large data with large models got us a shortcut to reasonably intelligent systems, though their robustness is debatable.
I have to interject again. I can't stop myself. I can't help myself. That is assume. I mean, your point about DNA encoding that amount of information assumes that we know everything about the DNA, and that is simply the source of compression or information passage. Is that extremely obvious, or?
Yeah, I mean, well, first of all, most of the DNA doesn't go into sorting out our brain. It has to deal with our liver and all
Many
that
other
other
things.
stuff. But so it's just a very small amount of information is used to initialize us, right? That's all I'm saying.
As a non-biologist, I think more about how many degrees of freedom are there in the quantum sense, but maybe
Oh,
that's a different topic.
Yeah,
It's
I don't
not
think
relevant.
that's relevant. Yeah.
Okay. You want to get closer to the mic or make sure it's on?
Okay, yeah, now it's on, sorry. Yeah, so just riffing on what Surya was saying. So LLMs are, they're very data and energy intensive, but this information lattice learning technique that I was just describing is an alternative that is much less kind of resource heavy. So the example I was giving was with learning the laws of music theory from just 300 chorales by Johann Sebastian Bach. So it's a nice example where you can be in the very tiny data regime. Likewise, we can achieve human-level performance on MNIST using just 4 examples of each digit, so literally 40 data points rather than 60,000 like is traditional, et cetera. And so that's one kind of path towards this intelligence that can be perhaps more data efficient. Likewise, that same technique is also very energy efficient. So like one of those music decomposition operations that I was showing is roughly 4 orders of magnitude less energy than a ChatGPT query. So again, we're much less energy, much less data, and able to achieve certain capabilities. So I think if we expand this armamentarium of algorithms beyond LLMs and related AI techniques, maybe we'll come up with things that are more kind of human-like in that respect. And coming back to this broader question that Karthik posed, so I've been working with my colleague Aaron Barbet, who's a theoretical and experimental neuroscientist. And so what we've been doing is taking many humans and doing fMRI plus tractography studies of them and trying to find the neural correlates of human intelligence, individual differences. And that joint structure function modeling seems to be fairly predictive of human intelligence. And it turns out that there's certain properties like small worldness in the brain networks, modal controllability, various other things that are the core features of making those predictions. And so again, that by itself, I think, is suggestive that there are kind of computational kind of underpinnings of human intelligence that we can characterize, whether it's related to information flow, whether it's related to the dynamics and control that's happening in the brain, and so on. And so I'm very hopeful to answer that broader question very much in a computational sense.
I just want to add one thing. If you talk about general intelligence, we humans can do science, those machines cannot do science, and I think it's not just a technical thing, there's something missing, especially we will need to know what is our fundamental drive to explore and to want to understand something new. I think that is still missing, and there are a few other things that are missing at that level. So how and why humans understand something and so on. We completely don't understand that and what that would even mean for machines. So I think this general intelligence, common intelligence, okay, but I think there's still a lot of understanding missing when we want to apply those systems to science.
Thank you very much. Chaozu. Push it up.
Well, it's hard to go beyond what the panelists have already said. Great points that I don't think that I can make predictions, right? Because all the predictions seem silly in 5 or 10 years. But about the limitation, I wanted to say that, you know, beyond data and beyond model, there's another limitation, that is the lack of evaluation criteria. So when you ask the question of when will AI replicate human intelligence, what are we talking about? What is the gold standard that, you know, if we reach there, we can safely say that this is, you know, success. If you're talking about, you know, AI surpassing human intelligence in isolated tasks, like AlphaGo, for instance, it has already happened. AlphaFold has already happened, right? When, you know, we hear these talks, you know, our speakers increasing the bar over again. So I think that generating new research ideas is also going to happen very soon. So when we talk about AI replicating human intelligence, we need a test, which we don't really know. And that, I think, is the biggest limitation right now.
Thank you very much. So the next question is, I know, somewhat vague and maybe not very deep, but I think it still needs to be asked, right? Because as we heard yesterday, you know, we can all have our high and mighty thoughts, but we need to be able to communicate, right, to people who don't understand AI or science, and maybe they're responsible for policy, right? So is it possible for AI systems to produce Nobel Prize type discovery of new phenomena, as this usually goes against conventional wisdom? Would it be able to produce a hypothesis contrary to most data that it's likely to see, right? And I think the answer in the future is probably yes, but let's talk about the near term, right? Let's talk about 3 to 4 years. And any of you can take a shot at it.
I can jump in. So I think, I mean, the most recent year of Nobel Prizes is already suggestive that AI can play a strong role, whether it was the biology or the chemistry Nobel Prizes, right? Both had some kind of element of AI in them.
What about the physics Nobel Prize?
Sorry, I misspoke. The biology and the physics. Yeah, sorry. But what the other one that I wanted to take up was actually the economics Nobel Prize recently, Daron Acemoglu. And so he often talks about, I mean, he does a lot of work. His productivity is quite crazy, but a lot of his work is focused on institutions and the roles they play in societies, whether democratic or autocratic, and et cetera. And I think that actually is perhaps the one of the Nobel Prizes that's most relevant to policymaking for AI going forward. I think we want to think through the way Daron describes like how we structure our institutions such that they can support a variety of ideas, so that 1,000 flowers can bloom, as it were. Because in some sense, we've fallen into this trap, it seems, that the hyperscaling paradigm is the only thing that anyone is investing in. But there are all these other algorithmic ideas, like was just mentioned. In 5 to 10 years, we don't know what will happen. And so when we're in this setting of deep uncertainty, I think we want to kind of hedge our bets, be less confident, like Surya was describing in a technical sense, but very much in a policy sense as well. So, you know, kind of have that portfolio of different approaches, and that I think will really help as we go forward on the policy side.
Thank you very much. But a small modification to my question, right? I'm sure AI is going to be used in probably every Nobel Prize discovery forward, but the question was, can it actually make that be the biggest component of it? Does your answer change?
No, I mean, I think AlphaFold was largely an AI Nobel Prize.
But they gave it not because it discovered something, it's because it helped a lot of things, right? So anyway, it's a minor point, but any others want to take? Yeah.
I'm pretty sure that this is possible in the next few years. I'm not sure that it is done with large language models. I'm not sure whether, for instance, for physics discoveries, that everything that humans have written down is actually useful. I think what is more useful is a system that can explore in a simulated or real world with some trustworthy simulators and can try to make discoveries there. For instance, imagine discovery of new super-resolution microscopes. Super-resolution microscopes got a Nobel Prize in chemistry a couple of years ago. I don't see any reason why we cannot, in a few years, discover completely new concepts for super-resolution microscopy with those hardcore exploration AI techniques. So I'm pretty sure that AI can discover Nobel Prize-worthy ideas in the near future in physics and chemistry.
You said simulators, computational discovery. MICD endorses those. Thank you. For any other quick thoughts on that? Go ahead.
I have a slightly different approach. I think it can, but if it does, it's probably due to luck. So how many Nobel Prize winners have won the prize twice?
2 or something, is that
4.
correct? 4.
Only 4. Mary Curie, John Badin, Fred Sanger, and Linus Pauling, and his second was the Nobel Prize in Peace, so that really doesn't count, right? So if we really know, if we really have the secret of how to be creative to get Nobel, style, Nobel level innovations, why can't they win it twice, right? So it's not replicable, right? And AI is built upon replicability, right? We talk about, whether we can reproduce the results, whether we can reproduce all the algorithms, right? If the humans can't, then I don't think that AI can replicate it. So it may win once, but it's going to be luck.
Scale test time compute for humans to 2 lives, and then
Correct. Yeah, it's a NVIDIA issue. All right. Okay. So the next question is connected to phase transitions, right? And no offense to physicists, right? And I'm not quite a physicist, but I sometimes try to be one. We are very strong in analogies, right? Anything we see, we try to relate to something we learned in our first graduate class, right? But barring that, what are the true connections between discovery or novel insight to phase transitions? Are these just anecdotal? Or is there something much deeper?
Yeah, I mean, I kind of spoke about this in my talk. So it seems to us that that there is this phase transition with respect to size scaling of LLMs and related large AI models. And it seems to us it is very much a true phase transition. It's not a mirage like Sanmi, Koyojo, and others argue. And so, I mean, not that both cannot be true. Like there can be a true phase transition and a mirage in some sense, but it does seem to us that there is exactly this phenomena. This emergence is very much a property of system size as you increase it.
So your question sounds like you were looking for some kind of beautiful theory or framework that can tell us exactly, at this point, we can predict there's going to be some emergent, capability, or trying to understand why this happens, right? So I think that's probably the ideal case.
The emergence is the process, right? I'm talking about actual scientific discovery, right? Emergence is one of the things.
Yeah, so I actually say that emergent capabilities could be one of the things, including, all those reasoning things we have seen, or the creative things we have seen, or maybe if you read, news online, there's also all kinds of mistake behavior that we don't expect a language model will do, right? So I think something between theory and anecdotal. When I say it's not anecdotal, because all of the things we can reproduce. So I wouldn't say that's anecdotal, which means it's also promising, because if we know exactly how those models are trained and what compute, use what data, what a procedure, you can reproduce all those things you have, which shows the promise we're able to formulate something.
Okay.
So I'm more optimistic that, someday, of course, I think there's a long way to go, because now we're still, although people say we're still very homogeneous, we're all training transformer, using this kind of, method, but there's still a lot of variance going on. So if we're able to understand, how exactly we can train a model to behave in some way like that, I think there will be a path to help us to understand this phenomenon better. Yeah.
very real sense in which phase transitions show up all the time in high-dimensional statistics and even shallow machine learning, right? Like finding the eigenvector of a covariance matrix buried in noise, like the spike covariance model. There's a phase transition amount of data. So if it shows up in such simple settings, it's probably going to show up in more complicated settings. But another thing that shows up often is like saddle point dynamics, saddle-to-saddle dynamics. So oftentimes the learning in these high-dimensional systems, there's many, many saddle points in the error landscape, and so you can get as you're doing energy, error descent, you get attracted to a saddle point along the attractive submanifold, and then you get repulsed along the repulsive manifold. And each time you do that, you learn something new. And so you can see that very clearly in simple models and in real models that that's happening. And that looks like a phase transition. It corresponds to the learning curve, sort of plateauing, then dropping, then plateauing, then dropping. Each plateau is sort of the time it takes to escape from a saddle point. Then each drop is what gets learned when it escapes from that saddle point. And we have a theory paper coming out that explains all of this soon. Yeah.
If I push back on that a bit, right? So we use learning in a lot of contexts, right? But in many contexts, some of the things you described is an L2 loss or something, right? So is that washing away a lot of meaning? I mean, I appreciate everything you said, but are we sometimes putting more emphasis on some simplistic settings?
Yeah. I think in some weird sense, we've now equated learning with the drop in some loss function.
Exactly.
Whether L2
That's
or something.
precisely was my point.
And the question is there some more sophisticated notion of learning than just drop in some scalar loss function? And I think there is. There's sort of grasping the underlying structure of a domain, suddenly figuring out reasoning paths that you didn't know before. We use drop in next token prediction as a proxy for these things, but is there another way to get to them? That's, I think, a very deep question, and I think we need to search for other ways to get to them.
Correct, and that's really been my pet peeve, although all the theory is incredibly beautiful. Any other takes on that? Yeah, go ahead.
One short comment on emergence. So there are basically two different types of discoveries you can do in physics. The first, the fundamental discoveries of new physical laws. For instance, I don't know, Schrödinger equation or standard model or neutrino oscillation, those are fundamental discoveries. And second, you have emergent discoveries. Those that are completely described by Schrödinger equation, Maxwell equation, but you don't see them in the Schrödinger equation. You only see them when you build a complicated system and then something very weird happens. And I think the second type of discovery, this emergent discovery, is much, much easier for AI to reach in physics and chemistry, actually.
Very encouraging. So you're going to show us something more next year, right?
If you think about gravitational wave detectors and so on, those
Correct.
Everything is described in Schrödinger equation, Maxwell equation, but you don't see it there, that you have to put everything in this way, then get these extremely sensitive devices.
So, wonderful perspective. Any other takes on this? All right. So the next question is closer to my heart, and I think some of you are already doing this, but I do want to, bring it up. So principles of information theory and statistical mechanics allow us to understand emergent phenomena from simple rules. For instance, from the molecular scale to mesoscale, things like that, right? And in physics, those things are, I think, much more concrete, right? So, where did I lose? Yeah. Is there hope to build a similar level of understanding for AI systems conditioned on the argument we just had, right? I don't want to be, slave to MSE or something like that, right? So something deeper that, can be much more comprehensive in how it's describing learning and other things.
I think so. I mean, the key insight from physics is that the connection from the microscopic to the macroscopic, right? And there's certain questions that just aren't worth asking or even answering, like what is the detailed dynamics of every single molecule in a gas? But there are other questions that involve emergent properties like pressure, temperature, volume, and so forth, where you can describe laws, right? And so these are macroscopic states that we can reason about and are worth reasoning about, and we can do it, right? So then the question is, in a learning process, we don't care about the in detail trajectory of all the weights in a neural network, but what are the macroscopic order parameters that we should care about? And we need to do a lot of work to understand that. In so-called mean field systems, where roughly everything's interacting with everything else weakly, we can extract these order parameters. We can write down dynamic equations for them. It's called dynamic mean field theory. we can get theoretical predictions that match numerical experiments. They even lead to ways to scale the systems up, like various extensions and say the mu-p parameterization, stuff like that. So it's the key insight is what is it that's worth explaining, and how do you write down equations for it? That's the key.
Yeah, that's a really good perspective. At least the way I think about it is, when we're exploring physics, right, we're exploring the real world. That is the thing, right, that matters because it's there. But I feel if you're talking about things like computational intelligence, we haven't built anything that is computationally intelligent yet or even close to it. So we're trying to cook up some very imperfect things and trying to learn. But at least my hope is someday we'll be able to build an abstraction architecture that is maybe closer to the real thing. And then all of these theories might start making a lot of sense, right? So just like looking at physics problems. You can respond to that or the other question I had.
Sure. Yeah, I mean, I'm happy to jump in because I think the epistemic kind of background of physical theories and phenomenology is a little different than those of engineering systems theories, right? And physical theories are meant to describe things, whether your abstraction is to go from micro to macro and so on. On the other hand, there's a myriad possibility of things that you can build as an engineer, and so the kind of game you play is trying to abstract things such that you capture their key properties, but ignore the things that are largely irrelevant. And then you prove theorems once you establish that kind of closed deductive system. And it seems to me that one of the areas in AI that could really benefit from such engineering systems theories is how to connect different models into larger systems. Right now, there's not a good way to reason about building compound AI systems out of several individual models. When you think about agentic AI interactions, again, there's not a very good kind of principled way of building those things, et cetera. And the kind of engineering systems theory approach, whether from control theory or information theory or elsewhere, is about building these block diagrams and knowing how the pieces fit together and so on. And I think that's really one of the big powerful ways we could use those going forward.
Takes?
Well, I'm not a physicist, but since this is Karthik's favorite question, I wanted to pitch in a little bit. So I think, as the AI researcher, I think our research has already been absorbing insights from, physics, from general science. For instance, that, when we worked on graph neural networks, our approaches have been heavily influenced by complex systems and such. If you think about representation space, right, of data, right, if you interpret every data point as particle, then you can interpret the relations, the distances as gravity, right? And then you can actually use that to understand the dynamic system of how the data, how the information, right, is evolving in that space. So recently we did the work. We gathered all the publications in AI and data science fields in the past 50 years, and then compute the high-dimensional representation, and then map that down to two-dimensional representation, and then show how the topics evolve over time, and we can measure the conditional entropy of how much novelty are there every year, and that gives us very surprising findings. If you look at, for instance, in the year 2011 to 2014, it's actually depressing that there are lots of papers, but none of them are actually increasing, the cross entropy. And then thanks to deep learning, and now thanks to large language models, then you can actually see a lot of variance. And I think those phenomena will actually really benefit from understanding the physical space of information.
All right, so I have a whole bunch of questions from the audience. I'm going to pick one. And I think this all of you can take a quick shot at, right? So the question goes, can you walk us through the different schools of thought today regarding building intelligent knowledge creating AI and which ones you're aligned to, right? So try to take your guess. Maybe not everyone has to answer, but whoever wants to take a shot. So if you want to build knowledge creating AI, if you're given, say, $1 trillion to do that today, which direction are you going to take?
Building on the point I was raising about not putting all one's eggs in one basket, I don't think it's a single approach. Nor do I think most people in cognitive science or neuroscience think that there's a single kind of approach for intelligence. If you look at biology itself, the armamentarium of biology is very broad. Like C. elegans works differently than mammalian cortex, works differently than these micro wasps that are pretty amazing, et cetera. So, again, I think I would challenge the question itself that I don't think there's a single paradigm that will be that solution to everything. And so we do need that broad portfolio.
Yeah, so if I had $1 trillion, I would honestly run a grant program that allows people to do anything except what everybody's doing right now. So no scaling up, no gigawatt data centers, no large data sets, nothing. Go back to the drawing board and really think about the deep questions, like how does the brain do 20 watts? How does the brain do local learning rules without backpropagating across the entire brain? Credit assignment problems like that. How do we learn with very little data? How do we teach machines without minimizing a loss function? These are very profound, fundamental questions, and we're not spending enough time thinking about these, and myself included, right? We get, we have students who need to graduate and stuff like that, so we try to create sensible projects for them. If I assigned a student like the problem of how do we do local learning rules, I'd destroy their career, right? But with us, with tenure, we have time to think about that. I mean, we should be thinking about that, but we don't have time to. So I would use the $1 trillion to buy many, many people freedom. And it would have to be many, many people because nobody has the right answer right now. Yeah.
Want to support that approach, right? If you have $1 trillion, can you hire me to build that?
Done.
Right. I think another way to state that is that, I think we want to increase the entropy of research, right, to really embrace the diversity and different problems. Right now, if you look at how large language models is driving our research, is actually decreasing the entropy of the research areas rather than increasing. So many people spend their talent on, a very focused questions like what you asked. So should we pick A? Should we pick B? Right? Should we, use transformers or other, architectures? But there are lots of diversity of problems out there, right? And then we really need to invest in those and try to have the aha moment so that ideas will actually suddenly emerge into Nobel Prize ideas.
Okay, great.
The question was about how can we build a machine that can increase knowledge or can give us new knowledge. That doesn't mean that the machine understands the knowledge. It just means that we get the new knowledge and new discoveries. So maybe it's not even necessary that there is a machine that knows everything. Maybe we can think about it differently. For instance, completely free exploration. You maybe want some intelligence there, but fundamentally it's not clear to me that answering your question requires that the machine itself is specifically intelligent. And that is one point. And the second point, I think we need those, at least in physics, those very clear verifiers, either simulated world or robotics. And there are a lot of extremely cool works in the field of material science, completely closed loop labs where robots drive around and do crazy stuff. And having that in physics would probably be very cool.
Absolutely right. I mean, simulators, verifiers, surrogates, I think. Any other cracks on that question?
I feel like, so if you want to really achieve that kind of level, human intelligence with knowledge creation, it will require us to work with people we usually don't work with before. So which means that we have to jump out of, our comfort zone and then trying to build connections or collaborations with people who are maybe also don't get used to work, for example, like me, computer scientist, right? So I think that will need a lot of initiative or, new kind of effort to build such kind of environment and platform to do it. Yeah.
All right, so another question that's approaching the same question from the other side, because there are graduate students who are thinking about, okay, what can I do in the next 4 years, right? So the question is, if we had to make a decision today, you can't punt it, right? Is the path to, where is that question? Artificial superintelligence probably is using convolutional diffusion models and transformers. Would you place, a good amount of faith in it? If you had to make a decision today, right? And you had to develop something very quickly.
And the level of resources that have already gone into it, it's probably the one that will pay off in the short term. But I think that's a little bit of a path dependence in terms of investment.
Right.
So I mean, I think that's definitely I do some consulting for Rand Corporation, and we wrote this little policy piece recently, which was about kind of many paths to AGI. And I mean, it was making that, portfolio type argument, but it was also making the argument that hyperscaling is already kind of at a place where a little bit more hyperscaling might help, or it might be that requires huge, like multiple orders of magnitude to get there, and it's hard to predict in certain ways. And so that's where this kind of plateauing and emergence argument that I was describing in my talk kind of comes into play. Like the core question to ask as a student is, do you feel like you're at the just before an emergent point, or are you at a just after an emergent point where you're in a plateau? And I mean, it's hard to know that when you're locally in it. But as you're thinking about research strategy, I think that's a lot of what one should think about. Like, when you're looking at theories of creativity, when there's lots of low-hanging fruit in a domain, you can make a lot of impact. When a domain is already well characterized, that inspiration set is very large, like things are already filled up, the spheres are already packed, then it's much harder to make an impact. It's much harder to be creative. So, starting your own new fields is often a good strategy if you can do it.
I feel like it's enough for you to make some change on architecture. Like a lot of people are doing that now, right? So in addition to transformer, CNN, right? So this MOE is a mixture of expert. It's not like done, in a longer period. It's actually done in a pretty short time and then find super helpful, like GPTs, using this architecture. So I wouldn't suggest people just say, I'm gonna choose the thing and then just work on it. I definitely would suggest my students spending time to think about alternatives, which could be super fruitful. So I think that's the strategy I would suggest.
So the next question may be gravitating towards you. There do seem to be, I don't know who's asking this question, and I don't know their background. So it was you. Do you want to state it, or? Yes. Well, okay. So go to the mic, and I will read it out, and you can correct me, right? So there do seem to be quantum effects involved in small cases of biological and cognitive systems, usually when a very large search space is involved. The process uncertainty often accompanied with heat generation and checkpoints and error correction, evolution places around them. So does biology ride a thin line between P and NP problems, and will we need quantum chips to address them? Did I get most of it? You want to switch on the mic, which is why I gave you the time.
Sorry, I'll switch it on. Okay. I was just, when I say do we need quantum chips, I just mean at small points. It could be like 90% is traditional computing, but at very, very tiny point of performance, you just cheat and pull an analog computer and then go back and do traditional computing.
Question, but
yeah, I think for like getting to AGI, I don't think we need it. In biology, there's very few places where quantum mechanics really plays a role. One is in the first steps of vision. It's known that we can detect single photons. So the absorption of a single photon by rhodopsin is a fundamentally quantum mechanical event. But then after that, it gets amplified and cascaded through a photoelectric multiplier effect. The other is photosynthesis. But after that, we're operating at room temperature, right? Our quantum computing colleagues are working so hard to cool their system down to way below room temperature. So it's almost impossible to imagine that quantum coherence is maintained over any long time scale at room temperature and you know, the internal cellular environment is chaotic and lots of molecules juggling around. So I don't think there's any role for quantum for AGI. Whether there's a quantum advantage, for example, in high-dimensional optimization problems, that's an open question that people are working on at the moment. But there's also very few algorithms for which there's a known quantum advantage as well. So, but that's outside of AGI. That's a different, like solving optimization problems in a different way.
Right, so one question for all of you, and it could be very quick. So what discovery in your particular domains, if produced by an AI system, would make you go, aha, that is incredibly innovative? I want to start with you. Chaozu.
As mentioned, if I can prove P equals or P doesn't equal to NP, that would be a hard moment, but that would be probably too big. Human AI collaboration is one thing that I wanted to mention, that how if AI and human can achieve complementarity, that if there is the clean test that shows that the sufficiently trained AI and human can actually perform together better than AI itself and than human itself, then I would consider that as the hard moment.
You've probably already had a few, but still.
Well, there are a lot of open questions in physics. For instance, we don't understand how galaxies rotate, which is kind of weird. So that would be if AI can come up with a coherent model that describes the rotation of galaxies together with all of these other effects, which is currently described mainly by dark matter theories, which have huge problems otherwise. If there can be a coherent theory, that would be absolutely amazing. There are other things, for instance, what is very important currently, quantum computers have these huge problems that you need error correction, and if you find efficient type of error corrections, which people are working on, that would not only be immediately impactful, but also have quantum computers coming from 50 years in the future, maybe to 5 years in the future. That would be amazing. And other, what I find interesting, other ways to observe the universe in the largest and smallest scales. If we can find enormously much better systems, that would also be such an aha moment, maybe.
Yeah. Out of curiosity, are you doing something on quantum error correction? If you are, I have some ideas. Anyway, yeah, let me take like culinary as an example of a domain. So, people have been cooking for a long time. And one of the things that seems to have emerged is what people call the Dorito effect. You can optimize for flavor, but not for other factors of human well-being. And so if we could be very kind of personalized such that we're improving human health in broad senses, human well-being in broad senses, as well as sustainability and supply chain resilience, kind of all of that at the consumer point of recipe design, I think that would be really compelling. Could have like large-scale behavioral change, just improve everyone's health and well-being.
I thought you might give an answer on the other end of the spectrum, but you went to the other end, but impressive.
I think these are all fantastic examples and would be highly impactful. But they all have the flavor of searching in some search space that we've already defined and we kind of know, and then finding stuff that we can't find because we don't have the capacity to search through it. I'd be super impressed if AI could find a new concept that we currently have no name for whatsoever. And that's been done in the past by humans, right? Like incredible leaps of insight, like, I hate to make Einstein the bar, but Einstein and his gravitational equivalence principle, where he thought about somebody in an elevator that's accelerating in outer space, they would feel like they're on Earth. And so he equated the gravitational principle, gravity with acceleration, and then came up with the curvature of space-time. Like, that was brilliant, right? And it involved concepts that we couldn't even name, like curvature of space-time at that point. So I would be extremely impressed if we could do that. I'm not sure that the combination of learning and search that we have at the moment can do that.
Fantastic. Same with calculus and Newton, right?
Yes.
Sort of.
Yeah.
Those are all great things. I'm not sure what I can add. I guess I'll just add when AI tells me that it reaches singularity and it proves by itself.
Oh, wow. Okay, that's a high bar, but okay. The other question that I have is, LLMs and agentic systems use nearly all of humanity's writings and wisdom. Is it necessary to rely on human knowledge, or can we bypass human biases in the near future? And it's kind of related to the auto hypothesis generation, which is not how physics is actually done, as was discussed. And any of you can take a shot.
I don't think that's true. There's a lot of human knowledge that's not in training data. So it's largely kind of data that's coming from written texts, things that are recorded, right? There's all kinds of things, cultural artifacts. I mean, a lot of stuff that's not captured that's relevant, and especially when thinking about AI alignment, you know, things are very kind of driven by certain moral theories that are not so general, and so like I would challenge the kind of the premise of the question that we've already, you know, gotten everything that humans know into these systems, but like suppose one takes that as an assumption that, you know, you've actually captured a lot of human knowledge. Is that enough to do things beyond that? It seems to me that it is, because a lot of creativity is combinational, it's compositional, and even these transformative creativity ideas, they're about kind of breaking knowledge and kind of creating new things. So even the Einstein example, like it is in some sense kind of taking things, breaking certain pieces of them, and then adding them back in. So like it seems to me that those can be kind of starting points for even the highest levels of transformative creativity.
Mario?
Probably, it's probably field dependent. I think in physics, or in chemistry, when you have virtual simulators or robots in the lab, I'm not sure it's really necessary or actually useful to have human knowledge. Maybe in bio this is very different because you don't have those simulators. Why I think that we could try to start from tabula rasa, completely from scratch, is what David Silver and DeepMind has done with Go, with AlphaZero. Was way better than AlphaGo. AlphaGo was trained on human games and then self-played, and AlphaZero was completely trained from scratch and reached way higher capabilities. This is an enormously small universe, but maybe this is scalable to some larger fraction of our real universe. So I think there's a lot of potential in this completely tabula rasa, and not thinking too much of what human scientists have already done.
Yeah, it's a very good point, except I want to push back a little bit on that in the sense that, yes, there are some physics problems where you have simulators that are fast and reasonably accurate, and some physics problems where you can observe the robot can do things. Correct me if I'm not a physicist, but in many, in fact, I might say almost all of physics, you don't have accurate and cheap simulators, and it's very hard to measure things. So would your answer change in that context?
One part where we don't have good simulators are large quantum system. That means then also everything that goes in material science. But I would call this chemistry. So I think in physics it's much easier. Okay, no, that's not true. In high energy physics they also have enormous problems with having reliable simulators. There are fractions of physics where it's possible, and I think there we could try this completely tabula rasa. In other regions, that's true. It's not only bio where it doesn't work. There are also parts of physics where it might not work.
It was a cooked up response because it's an existential thing. The reason why 200 faculty in MICD exist is because cheap simulators don't exist for that physics, right? Anyway, all right, so we're close to time, so I will monitor the questions, but my last one, I think all of you can take a crack at it if you want. Simple, AI that understands, what does that mean? And how can we verify? How can it be used? There are 3 questions in one. You can maybe take just the first one if you want. Maybe we go from this direction. if you want.
So I spend a lot of time thinking about the evaluation nowadays. I feel like I probably will take the verification aspect. I think the existing evaluation paradigm, which means that you build a lot of benchmark and to test a specific skill, or maybe even a wide range of them, will not go a long way because they become very strong. So we really have to think about, for one, how does evaluation firm going to look like in the future, right? So we cannot just always say, let's do the web checks and to the human, right? So that's not science, right? So we have to think about that. And the verification, reliability, trustworthiness of those models will also be quite important. I'm sure a lot of people are working on that, but I think that's also something we should think more. Yeah.
Beautiful set of videos on YouTube where they ask professors to explain something to like a 5-year-old, then a junior high student, a high school student, a college undergrad, then a grad student, right? And the ability to explain the concept at various levels of hierarchical organization, abstraction, coarse grained levels, and so forth, I think that's when you really understand something. And so, and related to that, Feynman also had an interesting point on understanding. Like, let's say for fluid mechanics, you could only predict the future of a fluid flow by numerically evaluating Navier-Stokes equations. You'd be loath to say that you understand fluid flows in any sense. You can also we have a lot of scenarios in which you can intuitively explain what a fluid will do, right? And qualitatively predict the future. So I think this kind of being able to explain something in many, many different ways constitutes understanding. And I think we might need benchmarks for that, for LLMs or whatever systems we have. And then I would think they probably understand things, and especially explain it in ways that are not in the training data. And I think one of the biggest problems we have in ML right now is that we don't know how to evaluate systems that have read the entire internet. And such systems can fool us into thinking they understand things deeply, but they probably don't. And we need better ways to evaluate these systems. And what is out of distribution when the training distribution is the entire internet? That's another big problem.
Selps and Barocas, they had this paper in a law review journal quite a few years ago. They kind of were discussing interpretability and so on, and they kind of distinguished two dimensions. One is inscrutability, and the other is non-intuitiveness. And inscrutability is the commonly kind of discussed aspect of AI. Can you understand what they're doing, et cetera? But I think the non-intuitiveness dimension is really the core of understanding. So if the laws that these systems learn and if they rest on intuitions that are not explainable to humans, perhaps there's some lack of understanding. If the decisions they make are not intuitive for humans in some other explainable senses, then there's lack of understanding and so on. And so it seems to me that this kind of intuition dimension, I think, is really the thing that will capture kind of AI understanding.
Yeah, we actually wrote a paper on a very similar topic on scientific understanding with artificial intelligence 2 years ago. And we looked very much into the philosophy of science, what philosophers, how philosophers understand the concept of scientific understanding. And one of the current model of that is that you have to be able to use some concepts of theory practically in a different context without using complete computation. So it's somehow very closely related with not using complete computation, which is very easy to see, for instance, in thermodynamics. You don't look at the individual particles, but you have those general properties that you also mentioned. So going away from this complete computation, we thought that in the end, the only way how you could verify is that the machine explains the new insights to a human, because you cannot really verify what the machine is doing internally. But this teaching, what you now also mentioned, I think is extremely good as a test and will be super, super useful in the future. Because, for instance, we have now a number of superhuman solutions in a bunch of different experimental physics settings. We don't understand them. But maybe there's a program that understands it And then this teaching component will be extremely important, that we have such models that teach us what those new experiments and those new physics paradigms mean.
Many of us consider AI as black boxes, not understandable, and humans are. But in fact, human minds are black boxes too. It's very hard to understand. If you have two teenagers at home, you know what I'm talking about. You know, in our recent work, we're trying to use AI to actually help us understand humans behavior and decisions. And the idea is to, let AI come up with the behavior code, and that's the latent representation of, the motivations behind human behaviors. And then if the AIs and humans can take the behavior code and regenerate, the decisions of the humans, then we consider that as the approach. But still, the question is open. Does that really mean that it understands, right? So I think the word understanding is heavily loaded. It's probably needs to be more formalized to answer this question.
Thank you very much. Now, this was incredibly fascinating. Thank you so much to the panelists, and thank you to the audience for listening. So I do want to take a picture with all of you, so just be seated as you are, and somebody can now volunteer to take a picture. Ancho, can you? It's been a privilege to be part of this panel. So it is lunchtime now, and the same as yesterday. So speakers and panelists and volunteers are going to be in the West Conference Room for lunch, if you wish. All others, right across the road in the tent. Thank you very much again. So we'll be back in about an hour and 20 minutes. And please enjoy the posters over lunch.